Welcome to session 4 video. In this video, we are going to discuss Cayley-Hamilton theorem. Cayley-Hamilton theorem states that every square matrix satisfies its own characteristic equation. Any square matrix, that is all square matrix, satisfies its own characteristic equation. This is one line statement. Now we are going to see what are all the uses of Cayley-Hamilton theorem. By using Cayley-Hamilton theorem, we can find inverse of a non-singular matrix A and we can find higher integral power of A. That is, using Cayley-Hamilton theorem, we can find A power minus 1 and higher power of A. That is A cube, A power 4. That kind of powers we can find. Let us discuss the problems under Cayley-Hamilton theorem. Problem number 1. Verify that A equal to 2 by 2 matrix is given, satisfies its own characteristic equation and hence find A power 4. Matrix A is square matrix, 2 by 2 matrix. We want to verify that it satisfies its own characteristic equation. The statement clearly intimates that it is Cayley-Hamilton theorem. So, in the question, we have the word characteristic equation. So, first we want to find characteristic equation of A. Since it is 2 by 2 matrix, already we discussed how to find characteristic equation for 2 by 2 matrix. It can be simply written as lambda square minus S1 lambda plus S2 equal to 0, where the unknown S1 equal to sum of the diagonal. Sum of the diagonal elements are 1 and minus 1. You have to add it, then you will get 0. S2 formula, determinant of A, take determinant of A. Determinant of A can be found by using the general formula. That is, the determinant of A equal to 1 into minus 1 is minus 1, minus 2 into 2 is 4. So that totally, after simplifying the answer, we get minus 5. By using these two values in the characteristic equation, we get lambda square minus 5 equal to 0. Now we need to verify that the characteristic equation satisfies its own, the matrix satisfies its own characteristic equation. That means instead of lambda, you have to substitute A. Then we get A square minus 5i equal to 0. Now we are going to verify whether this equation is true or not. How do you verify? In LHS part, we have A square minus 5i. We need to find A square. A square is nothing but A into A. Product of two matrices. A is given matrix, given 2 by 2 matrix. You have to multiply these two matrices. We get 5, 0, 0, 5. Then you have to use this value in the equation A square minus 5i. Then we get 0. That is, the matrix becomes null matrix. Therefore, we got the answer 0. That is A square minus 5i equal to 0. It says that the matrix A satisfies characteristic equation. So we verified Cayley-Hamilton theorem. In the next part, we are going to find a power 4 without calculation of the product of matrices. By using this equation, we are going to find a power 4. In this equation, since already this equation is true, we verified already. So consider this equation again, a square minus 5y. Then keep a square in LHS side, bring 5y into RHS side. Then we get a square equal to 5i. We need a power 4. So both sides you have to multiply with a square. Then LHS becomes a power 4. RHS becomes 5a square. Already we have the value for a square. Substitute here. We get 5 into 5, 0, 0, 5. So after multiplication of these two values, we get 25, 0, 0, 25. This is the value of a power 4. Now we are going to discuss second problem. Find the characteristic equation of the matrix A given A equal to 3 by 3 matrix. Hence, find a power minus 1 and a power 4. So, after finding characteristic equation, we want to find a power minus 1 and a power 4. Since we already discussed Cayley-Hamilton theorem uses to find the inverse of the matrix and higher power of the matrix. Now we are going to find characteristic equation first. The given matrix is 3 by 3 matrix. So general form of the characteristic equation as lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0. You may follow the general form, this form, determinant of a minus lambda I equal to 0, or the simple form lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0. Since S1 formula, sum of the diagonal elements of A, the diagonal elements are 2, 2, 2. So addition of these three 2's, we get 6. S2 formula, sum of minus of the diagonal elements of A. We want to get the minus of each and every diagonal. Since diagonals are 2, 2, 2. So in the matrix, try to find the minor of each diagonal elements. Then we get the addition as 9. Then S3 equal to determinant of A. We want to take determinant of the given 3 by 3 matrix. Then we get 4. Use S1, S2, S3 values in the general characteristic equation. We get lambda cube minus 6 lambda square plus 9 lambda minus 4 equal to 0. Now we can use Cayley-Hamilton theorem. No need to verify Cayley-Hamilton theorem. We can use it because the question is simple question. Using Cayley-Hamilton theorem, find A inverse and A power 4. So, by Cayley-Hamilton theorem, A satisfies its characteristic equation. That means, instead of lambda, we can replace A. So, A cube minus 6A square plus 9A minus 4 into I equal to 0. That is, in this characteristic equation, you have to substitute lambda equal to A. Then you get this equation. This equation is true. By Cayley-Hamilton theorem, this equation is true. From this, we want to find A power minus 1. So, you have to keep the constant term 4i in LHS side. Bring all other term into RHS side. It becomes 4i equal to A cube minus 6A square plus 9A. Both sides you have to multiply with the a power minus 1 for each and every term. Then you get 4i a power minus 1 equal to a cube a power minus 1 minus 6a square into a inverse plus 9a power minus 1. Therefore, 4a inverse equal to a square, a cube into a power minus 1, base same. So, we can add the power. 3 minus 1 becomes 2. So, a square minus 6a plus 9. A into a inverse is nothing but identity matrix I. Now, we need to find a square. A square value. A square is the product of two matrices, that is A into A. Multiply these two matrices, then we get 6 minus 5, 5 minus 5, 6 minus 5, 5 minus 5, 6. Then now we are ready to substitute every values because A is given matrix. Now we calculated A square value. I is identity matrix, 3 by 3 identity matrix. So now we are ready to substitute all the matrices in this equation. Therefore, 4A inverse equal to, in which you have to substitute A square value, A value and identity matrix value. Then simplify the answer, you get A inverse equal to 1 by 4 into 3, 1 minus 1, 1, 3, 1 minus 1, 1, 3. So we completed to find A inverse. Now we are going to find A power 4. Since A cube equal to 6A square minus 9A plus 4I. Both sides you have to multiply with A, then LHS become A for 4. RHS becomes 6A cube minus 9A square plus 4A. In which you have to substitute all the matrix values because A cube already we calculated. Then A square we have, then A value we have. Since A cube answer is 6A square minus 9A plus 4I, you have to substitute here. Then simplify the equation, then we get 27A square minus 50A plus 24I, in which you have to substitute A square, A and identity matrix. Then we get A power 4 equal to 86 minus 85. 85 minus 85, 86 minus 85, 85 minus 85 and 86. This is A power 4 value. In this video, we discussed about Cayley-Hamilton theorem and we have discussed some problems under Cayley-Hamilton theorem and we used Cayley-Hamilton theorem to find A inverse and A power 4, that is higher power of A. Thank you.